Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is plugging circuits. Our objective is to introduce the concept of plugging a motor and examine ladder logic diagrams facilitating or preventing this action from occurring. This lecture operates under the assumption you have watched the Reversing Motor Starters with Interlocks lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. As you'll recall, we ended the Reversing Motor Starters with Interlocks lecture on a bit of a cliffhanger in that I briefly introduced a reversing motor starter using push-button interlocking and put off a thorough analysis of the ladder logic diagram until another day. That other day is now upon us. This particular reversing motor starter using push-button interlocking exhibits a phenomenon called plugging, where the term plugging means the instantaneous reversal of applied phase sequence while the motor is running. Phase reversal develops a counter torque, and a plugging action can be used to bring a motor to a rapid halt or enable quick reversal of rotational direction. Note this reversing motor starter with push-button interlocking makes use of mechanically interlocked forward and reverse buttons that when one mode is selected, the opposite is deselected. Note the normally closed side of the mechanically interlocked forward push button acts just like a stop push button for the reverse circuit. Similarly, the normally closed side of the mechanically interlocked reverse push button acts just like a stop push button for the forward circuit. Push button interlocking should be used only in conjunction with mechanical and electrical interlocking and is intended to supplement these methods, not replace them. Note this reversing motor starter also includes mechanical and electrical interlocks as well. In the event of a jammed or slow on the draw contact carrier, these methods prevent simultaneous closure of both contactors. Recall that simultaneous closure of both the forward and reverse contactor constitute a dangerous phase-to-phase event to be avoided at all costs. The complementary protection methods ensure this event does not occur. In contrast to reversing motor starters using only mechanical and electrical interlocks, this particular reversing motor starter reverses direction immediately without the stop button being pressed. Allow me to demonstrate. Let's make some room by removing the primary schematic and zooming in on the pilot ladder logic. Next, let's ditch the ugly dashed mechanical interlock between the forward and reverse push buttons. The dashed lines are just going to make our analysis difficult. You're just going to have to remember that they're mechanically interlocked. Note, forward is green, reverse is orange. Consider the following scenario in which an operator presses the forward push button. The normally open side of the mechanically interlocked forward button closes and the normally closed side opens. Via the normally closed e-stop, the normally closed stop, the normally closed side of the reverse button, the now closed forward button, the normally closed R2 electrical interlock contact, and the normally closed overload contact, the F coil of the forward contactor would be energized. When the F coil is energized, its associated contacts change states. The normally open F1 holding contact in parallel with the forward button closes. The normally closed F2 electrical interlock contact opens, and the primary F contactor would close. Referring to our previous primary schematic, note that the applied phase sequence as provided by the forward contactor would be L1, L2, L3. The motor would experience inrush current and begin rotating clockwise. Once the motor reached rated speed, the inrush current would subside and level out at the full load rated current. If an operator were to release the momentary contact forward push button, the spring return would return it to its normally open deactivated state. Note that the now closed F1 holding contact maintains the energized state of the F contactor coil. This means the primary F contactor stays closed and the motor continues spinning in the clockwise direction. That's the point of the holding circuit. It maintains the last asserted state. While traveling in the forward mode, consider what would happen if an operator pressed not the stop button, but rather the reverse button. The normally closed side of the mechanically interlocked reverse button opens, and the normally open side closes. Via the now open normally closed side of the mechanically interlocked reverse button, the forward contactor coil is de-energized, and the associated contacts return to their deactivated state. The normally open F1 holding contact opens, removing the path in parallel to the forward push button. The normally closed F2 electrical interlock closes. The F primary contactor would open. Via the normally closed E-stop, the normally closed stop, the normally closed side of the mechanically interlocked forward push button, the now closed normally open side of the mechanically interlocked reverse button, the normally closed F2 electrical interlock contact, and the normally closed overload contact, the R coil of the reversing contactor would be energized. When the coil of the R contactor energizes, its associated contacts change states. The normally closed R2 electrical interlock opens. The normally open R1 holding contact in parallel with the reverse push button closes, and the primary R contacts would close. Note from our previous primary schematic that the applied phase sequence as provided by the reversing contactor would be L2, L1, L3. Phase sequence has been instantaneously reversed without the need of the stop push button. The motor would experience a substantial current draw, many times greater than that of normal inrush, and would rapidly decelerate in the clockwise direction and begin rotating counterclockwise. Once the motor reached rated speed, the inrush current would subside and level out at the full load rated current. If an operator were to release the momentary contact reverse button, the spring return would return it to its normally open deactivated state. Note that the now closed R1 holding contact maintains the energized state of the R contactor coil. This means that the primary R contactor stays closed and the motor continues spinning in the counterclockwise direction. That's the point of the holding circuit. It maintains the last asserted state. The E-stop, stop, and overload function as previously discussed for an ordinary reversing motor starter. It should be noted that the simultaneous actuation of both forward and reverse would disable both modes. However, upon release of the two buttons, the state of whichever button was last actuated would be asserted. By using push-button interlocking, this reversing motor starter makes it possible to directly switch from forward to reverse and vice versa, bypassing the stop intermediary. As alluded, a plugging event is characterized by a current draw many times greater than that of even inrush, a phenomenon already characterized by an intense but brief surge. For this reason, contactors intended to plug a motor must be sufficiently rugged enough to handle this event. Additionally, repeatedly plugging a motor can cause overload elements to trip early due to the cumulative nature of heat. Finally, the nature of the driven load must be considered when plugging a motor. A sudden reversal of a load with a large inertia could easily snap a shaft or otherwise damage the system. We'll discuss antiplugging circuits that prevent immediate reversal in a moment. For now, let's consider plugging a good thing. Not only does plugging a motor enable immediate reversal, it can also be used to our advantage to decelerate a motor. Note plugging can only be used to rapidly decelerate a moving motor, not lock it in place like a friction brake. Plugging, like DC injection, regenerative, or other dynamic methods we'll examine much later, can only decelerate a moving motor. Once the rotor stops moving, these dynamic methods don't work well, and mechanical means like friction brakes must be used to lock the shaft. Consider this motor starter that uses a rotational speed switch and plugging to rapidly decelerate the motor when stopped. Recall from the Switches in Electrically Controlled Systems lecture that a rotational speed switch is an electromechanical device affixed to a shaft that changes states when it reaches a predetermined rotational speed set value. For this application, this particular plugging switch is often called a zero speed switch, in that any rotational speed above 0 RPM actuates the switch to its opposite closed state. This particular motor starter is intended to run the motor in one direction only. However, notice the primary schematic uses paired contactors quite like a reversing starter. The forward F contactor is wired such that phase sequence as seen by the motor is L1, L2, and L3. The plug to stop P contactor is wired such that phase sequence as seen by the motor is L2, L1, L3. Since this motor starter is intended to be unidirectional, the plug to stop P contactor's only purpose is to decelerate the moving motor. Let's see how the ladder logic diagram incorporating the zero speed switch makes this happen. At rest, the normally open zero speed switch is in its deactivated open state. The plug to stop P contactor coil therefore remains de-energized. Note the complementary electrical interlocks provided by the normally closed P1 and F2 contacts. The purpose of these electrical interlocks is to keep the opposite coil de-energized when the other one is energized. This prevents the simultaneous closure of the F and P contactor. When an operator presses the start push button, the momentary contact normally open start switch closes. Via the normally closed e-stop, the normally closed stop, the now closed start push button, the normally closed P1 electrical interlock, and the normally closed overload contact, the F coil of the forward contactor would be energized. When the coil of the F contactor energizes, its associated contacts change states. The normally closed F1 holding contact in parallel with the start button closes. The normally closed F2 electrical interlock contact opens, and the primary F contacts close. Notice applied phase sequence as provided by the forward contactor is L1, L2, L3. The motor experiences inrush current and begins rotating clockwise. Note at speeds above 0 RPM, the zero speed rotational speed switch is actuated to its opposite closed state. The electrical interlock provided by the now open F2 contact, however, keeps the plug to stop P contactor coil de-energized. Once the motor reaches rated speed, the inrush current subsides and levels out at the full load rated current. If an operator were to release the momentary contact start push button, the spring return would return it to its normally open deactivated state. Note that the now closed F1 holding contact maintains the energized state of the F contactor coil. This means the primary F contactor stays closed and the motor continues spinning in the clockwise direction. That's the point of the holding circuit. It maintains the last asserted state. When an operator presses stop, the now open stop button de-energizes the F contactor coil, and the associated contacts return to their de-energized state. The normally open F1 holding contact opens, removing the path in parallel to the forward push button. The normally closed F2 electrical interlock closes. The F primary contacts open. Notice, while the motor is still rotating clockwise at speeds above 0 RPM, the closure of the F2 electrical interlock contact energizes the plug to stop P contactor coil via the still actuated zero-speed rotational speed switch. When the coil of the plug to stop P contactor coil energizes, its associated contacts change states. The normally closed P1 electrical interlock contact opens, and the primary P contacts close. Note the applied phase sequence as provided by the plug to stop P contactor is L2, L1, L3. Counterclockwise counter torque produced by the immediate phase reversal decelerates the motor. An operator can now release the stop push button. Once the motor reaches a dead stop, the zero-speed rotational speed switch returns to its deactivated open state and de-energizes the P contactor coil, and the associated contacts return to their deactivated state. The P1 electrical interlock contact closes. The primary P contacts open. This plug-to-stop contactor has brought the rotor to a complete stop without making physical contact. Note that while being plugged to stop, the start button is disabled via the open P1 electrical interlock. Only when the motor has been brought to a complete stop will the start switch energize the motor to spin clockwise. Additionally, note if the normally open zero speed switch failed to reopen at exactly 0 RPM, the plug-to-stop P contactor would remain energized. Not only would the motor rapidly decelerate, it would skip the dead stop and accelerate in the reverse direction. For this reason, zero speed switches don't really actuate at exactly 0 RPM, and instead actuate and deactuate inside an acceptable range, which is sometimes adjustable for the application. Once inside this predetermined acceptable range, the zero speed switch opens and de-energizes the plug-to-stop contactor. The motor, having been decelerated to almost a standstill, glides to a quicker halt than an ordinary free spin, all without making physical contact with the rotor. If the application warranted its inclusion, a spring-applied, electrically released friction brake can be included in this system. Note the friction brake's only purpose is to mechanically hold the position of a stopped rotor, not to decelerate a moving one. Deceleration is provided via plugging without the necessity of making physical contact. In this application, the spring-applied, electrically released friction brake would be released anytime voltage is applied to the motor, i.e., either in forward or plug-to-stop mode. Only when no voltage is applied to the motor is the electrically released, spring-set brake applied. The advantage of this staged non-contact deceleration via plugging and contact rotor locking at a dead stop via the friction brakes extends the life of the brake pads and is immeasurably cunning and cool, and don't you dare tell me it isn't. Note the last ladder logic diagram only enabled deceleration via plugging in one direction. If we wanted to plug a reversing motor starter, we'd need to upgrade our system. This particular ladder logic diagram enables bidirectional deceleration via plugging using a slightly modified method. Note this ladder logic diagram features two different aspects of the same rotational speed switch in rung 5 and 6. Rung 5 contains a normally open rotational speed switch that is actuated into its closed state at speeds above 0 RPM in the reverse direction. Rung 6 features a normally open rotational speed switch that is actuated into its closed position at speeds greater than 0 RPM in the forward direction only. These rotational speed switches in rung 5 and 6 basically bypass elements in rung 4 and 7 when they are actuated by the respective directional rotation. Let's see how these rotational speed switches, the mechanically interlocked reverse and forward push buttons, and electrical interlocks coordinate the activity of this system. Let's walk through the ladder logic diagram and see how this system works. First, let's ditch this ugly rung-spanning dashed mechanical interlock for the forward push button. Same thing for the reverse. It's just going to complicate our analysis. You're just going to have to remember that the forward and reverse push buttons are mechanically interlocked. Note the forward button is green and the reverse button is orange. If an operator pressed the forward push button, the normally open side in rung 1 would close, and the normally closed side in rung 7 would open. Via the E-stop, the stop, the now closed forward, and the normally closed overload contact, the coil of control relay CR is energized. When energized, its associated contacts change states. Holding contact CR1 closes, as does CR2 and CR3. Via the E-stop, the normally closed side of the mechanically interlocked reverse push button, the now closed CR2 contact, the R2 electrical interlock, and the normally closed overload, the F coil of the forward contactor is energized. When the F coil is energized, its associated contacts change states. The F2 electrical interlock opens, and the primary F contacts close. Applied phase sequence, as provided by the forward contactor, is L1, L2, L3. The motor experiences inrush current and begins rotating. Note at speeds above 0 RPM clockwise, ZSF is actuated to its opposite closed state. The electrical interlock, provided by the now open F2 contact in rung 7, keeps the R coil of the reversing contactor de-energized. Once the motor reaches rated speed, the inrush current subsides and levels out at full load rated current. An operator can now release the forward button. The spring return would return it to its normally open deactivated state. Note the now closed CR1 holding contact maintains the energized state of the CR relay. This means the primary F contactor stays closed and the motor continues spinning in the clockwise direction. That's the point of the holding circuit. It maintains the last asserted state. If an operator wanted to plug to stop this motor, they would press the stop button. The now open stop button de-energizes the CR coil. The associated contacts change to their deactivated state. Holding contact CR1 opens, as does CR2 and CR3. The now open CR2 contact de-energizes the F coil of the forward contactor, and its associated contacts return to their deactivated state. The F2 electrical interlock closes, and the F primary contacts open. Notice while the motor is still rotating clockwise at speeds above 0 RPM, the closure of the F2 contact energizes the R coil of the reversing contactor via the still actuated ZSF rotational speed switch. When the R coil of the reversing contactor is energized, its associated contacts change states. The normally closed R2 electrical interlock opens, and the primary R contacts close. The applied phase sequence as provided by the reversing contactor is L2, L1, L3. Counterclockwise counter torque produced by the immediate phase reversal decelerates the motor. An operator can release the stop push button, and the spring return returns it to its deactivated closed state. Once the motor reaches a dead stop, the rotational speed switch ZSF returns to its deactivated open state and de-energizes the R coil of the reversing contactor, and its associated contacts would change to their deactivated state. The R2 electrical interlock would close, and the primary R contacts would open. This motor has been effectively plugged to a stop without the necessity of making physical contact. You would find similar behavior if an operator were to press and release the reverse push button, and then press and release the stop push button. While being plugged to stop from the reverse direction, note that rotational speed switch ZSR in rung 5 would energize the F coil of the forward contactor until such time the rotor reaches 0 RPM. Note while operating in forward mode, if an operator were to press the reverse push button, the normally open switch in rung 2 would close, and the normally closed switch in rung 4 would open. Coil CR remains energized, however the F coil is de-energized. The associated contacts return to their deactivated state. The F2 electrical interlock closes, and the F primary contacts open. The closure of the F2 electrical interlock energizes the R coil of the reversing contactor via the still closed ZSF rotational speed switch. The associated contacts change states. The R2 electrical interlock opens, and the R primary contacts close. Phase sequence as applied by the reversing contactor is L2, L1, L3. As previously, counterclockwise counter torque produced by the immediate phase reversal decelerates the motor. An operator can release the reverse push button, and the spring return returns it to its natural deactivated state. The normally open side in rung 2 opens, and the normally closed side in rung 4 closes. At 0 RPM, the rotational speed switch ZSF opens. However, the energized state of the R coil is maintained by the normally closed forward push button, the now closed CR3 contact, and the F2 electrical interlock. The motor continues to accelerate in the reverse direction. At speeds above 0 RPM counterclockwise, ZSR closes when we find ourselves in a held reverse state, and the motor continues to rotate counterclockwise. Therefore, this ladder logic diagram not only enables deceleration by plugging to stop, it also allows quick reversal of rotational direction. You'd find similar behavior if while in reverse mode, an operator pressed and released forward. Up to this point, we've been discussing plugging as if it was always a good thing. Yes, plugging can quickly reverse a motor, and plugging can rapidly decelerate a moving motor, but plugging can also be an undesirable event for high inertia loads that can snap a shaft or otherwise mechanically damage the system. For this reason, anti-plugging circuits are utilized. Consider an ordinary mechanically and electrically interlocked magnetic reversing motor starter. My question to you is this: can an operator plug this motor? The answer is yes, and they will do it. If there is one thing I've learned throughout my professional careers as an officer, engineer, and educator is to never underestimate the capacity of soldiers, operators, and students to break things. Here's how. An operator presses and releases forward, and the motor and driven load come up to a rated speed. The operator presses and releases stop. And while the motor and driven load with large inertia is decelerating in the clockwise direction, they press and release reverse despite clear instructions not to do so. The applied phase sequence is immediately reversed and the counter torque snaps the shaft. For this reason, antiplugging circuits that allow a motor to be driven clockwise or counterclockwise from a dead stop, but do not allow a moving motor to be plugged, are utilized. Consider the ladder logic diagram of one such circuit. Key to the functionality of this antiplugging circuit is a rotational speed switch with two normally closed sides. Let's say the rotational speed switch has a set value of an acceptable 30 RPM, above which it is actuated into its open state. RSCCW in rung 1 opens at 30 RPM counterclockwise, whereas RSCW in rung 4 opens at 30 RPM clockwise. Note the electrical and mechanical interlocks prevent simultaneous closure of the forward and reverse contactor. If the rotor was at rest and an operator pressed the forward push button via the E-stop, the stop, RSCCW, the now closed forward push button, the R2 electrical interlock, and the normally closed overload contact, the F coil would be energized. The associated contacts change to their opposite state. The F1 holding contact closes, the F2 electrical interlock opens, and the primary F contacts close. Applied phase sequence as provided by the forward contactor is L1, L2, and L3. The motor experiences inrush current and begins rotating clockwise. Note at speeds above 30 RPM for this particular application, RSCW is actuated to its opposite open state. An operator can release the forward push button and the spring return will return it to its normally open deactivated state. The F coil remains energized via the now closed F1 holding contact. The motor continues to rotate clockwise. If an operator pressed stop, the F coil would be de-energized, and its associated contacts would return to their deactivated states. Holding contact F1 opens, electrical interlock F2 closes, and the F primary contacts open. If an operator were to release the stop push button, the spring return would return it to its deactivated normally closed state. If an operator quickly pressed the reverse button while the motor was still decelerating at clockwise speeds in excess of the RSCW set value of 30 RPM, note the still open RSCW rotational speed switch prevents the R coil of the reversing contactor from being energized. This anti-plugging circuit therefore prevents immediate phase reversal and a dangerous counter torque for this particular application. Only when rotational speed switch RSCW has dropped below an acceptable predetermined value of 30 RPM clockwise will the reverse push button assert the reverse mode and allow the motor to rotate counterclockwise. Long story short, these rotational speed switches are used to prevent assertion of the opposite mode when the motor is above a predetermined set value. Below these rotational speeds, the circuit works just like a regular magnetic reversing motor starter with mechanical and electrical interlocks. Alright, this about wraps up our introduction to motor plugging. Be aware that the rotational speed switch is not the only common input to a plugging or anti-plugging circuit. We've yet to discuss timer relays. Once we've gotten a basic introduction to the timer relay, be prepared to revisit plugging making use of this device. In conclusion, this lecture took a brief look at motor plugging, an instantaneous phase reversal event characterized by a counter torque that decelerates a moving motor and a tremendous surge of current. Plugging can be used to perform quick reversal of rotational direction or decelerate a moving motor without making physical contact. Plugging is only used to decelerate a moving motor. Contact methods, like friction brakes, must be used to lock a rotor in place. We discussed plugging to decelerate a unidirectional motor starter, plugging to decelerate a bidirectional motor starter, and an anti-plugging circuit that allows bidirectional rotation from at-rest conditions, however, does not allow reversal of a moving motor. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.